Hello and welcome to this Google Hangout on the STM32L4. My name is Nathalie Magnier. I'm working in ST Online marketing team, and I will shortly introduce this Hangout before giving the floor to our experts. The Hangout will last 1 hour. Stuart McLaren will first go through the STM32L4 product. Alec Bath will then go through the development ecosystem. And Bertrand Denis will manage your questions. Don't hesitate to ask questions using the Q&A panel during the presentation. And we will also let time at the end of the Hangout for any additional questions. Stuart?
Thank you, Nathalie. So we're going to be talking today about a new STM32L4. It's a ultra-low power microcontroller, which brings leadership, ultra-low power features, but also brings performance to the that's not been seen before in the ultra-low power microcontroller marketplace. Everything we're going to talk about today is available, so all the devices, the ecosystem, the kits, etc. go through in the presentation are available. So if you want to find out more information, I think we have some links in the showcase that you can go to. And also our distributors around the world also have stock of the products and can help support you with the products. We also have a range of seminars coming up in North America. Again, I think the link is in the showcase. So if you find what we're presenting today interesting, then you can come to the seminars. We have about 15 seminars, one-day seminars, starting on the 20th of October. So you can come and learn more about the STM32L4. So I'm now going to share my screen, and we'll move to the presentation. So hopefully you can see the first slide in the presentation. So as I said, we're going to be talking about the STM32L4. It's an ultra-low power microcontroller, and as we go through the presentation, I think you'll see that it brings true leadership in ultra-low power, but it also brings a level of performance that's not been seen in the low-power microcontrollers before. So it's built on a new architecture, and we needed a new architecture to bring, as I said, both the leadership in ultra-low power and bring high levels of flexibility so people can tune the ultra-low power features to their application and get the lowest power consumption in their application. But it also brings new levels of performance that have not been seen in the low power microcontroller market before. And we're able to do that through a combination of the ARM CortexM4 core, which of course has its floating point support and DSP support. But we're also doing that with some innovations within ST, including the ST Art Accelerator, which allows the part to run at full performance out of internal memories up to 80 megahertz. In addition to that, to address a broad range of applications in the market, the architecture also implements a lot of innovations and embeds a lot of smart analog and digital peripherals. And again, we'll go through those in more detail in the presentation. It also brings a high level of integration. In addition to the core and the broad range of peripherals, we have large memories, so it has up to 1 megabyte of flash and 128 kbytes of RAM, and also a broad range of safety and security features that are often needed in a low power application. It also does all of that in an extremely small form factor, as small as 3.8 by 4.4 millimeters. So you get a very high level of integration with the core, the flash, the memory, and the peripherals, but in a very small form factor. It also builds upon the STM32 ecosystem. So ST was a lead partner with ARM in the introduction of the CortexM cores in 2007. Since then, we've built an extremely broad portfolio with CortexM0, M0 Plus, M3, M4, and most recently M7 devices. with a very broad ecosystem of partners around the STM32 as well. So the STM32L4 benefits from that, and it also benefits from the pin-to-pin compatibility with the rest of the family. So people can move up and down the STM32 family and get the benefits of the L4, or if they want to move to a higher performance, they can move to an M7, or if they're looking for an entry-level microcontroller, they can use the M0, M0 Plus. So we're going to look in more detail at some of the new features in the STM32L4 that help with the power consumption and help with the flexibility that I was talking about earlier. No two ultra-low power applications are the same, and so it's very important when designing an ultra-low power microcontroller to design a platform that allows the designer the maximum amount of flexibility so that he can tune the microcontroller to his application and get the lowest power consumption. So we have a new shutdown mode in the device, and that goes down to a very low 30 nanoamps, but still allowing for I/O wake up. We also have an RTC that's available in all power modes, from the active modes right down to the VBAP mode. The VBAP mode itself goes down to a tiny 4 nanoamps, and we automatically switch between the VBAP mode and the normal mode when the VDD is removed from the device. So it'll automatically switch to the VBAP mode. There's also a charging capability in the VBAP mode, so when the device is running off standard power, it can charge a supercapacitor or alternative, so that when it goes into the VBAP mode, you have something to maintain the status of the part. As USB, again, that's quite common in many ultra-low power applications, and so we have full support for USB. But what's with the additional feature here that you do not need a dedicated oscillator for the USB functionality. So the USB can run off a 32 kilohertz crystal oscillator, and there's no need to add an additional oscillator for the USB functionality. We also have an internal oscillator with high accuracy. It's plus or minus 0.25%, and will operate across the range from 100 kilohertz to 48 megahertz. Another new feature is that the I/O levels are maintained even in low power modes, which means that if you set an I/O and then go into a low power mode, then you can keep the I/O level maintained even when you've got the very low power mode and optimizing the system consumption. So again, that helps keep power down. You don't need to be in an active mode to maintain those I/O levels. You can wake up the MCU with any peripheral, so it can be, and as we go through the presentation, you'll see there's a lot of communication interfaces, analog circuits and timers on the device, and it's possible to wake up the MCU from any of those peripherals. We also have another mode where the 32K bytes of the SRAM can be maintained in standby mode, and in that mode it's an extremely low 360 nanoamps, and you've got full 32K bytes of SRAM. So that helps if you want to wake up the device quickly and maintain a lot of state. You're able to do that and only consume 360 nanoamps. And finally, there's an external level shifter, so that if you're trying to talk to additional devices that are operating off different VDD supplies, then the device there's no need for an external level shifter. It's possible to talk to external devices and with VDD supplies down to 1.08. So we're now going to look at the ultra-low power modes, and as I was saying, one of the things we try to do is give designers the maximum amount of flexibility so they can choose the modes they need in their application and keep the power consumption down to the minimum. So we have the VBAP mode that we talked about just now, and that VBAP mode goes down to 4 nanoamps. You'll see for all of these modes we have two figures. One, the lower figure is without the RTC, and then the figure with the asterisk is with the RTC. So without the RTC, the VBAT current is down to 4 nanoamps. With the RTC, it's 300 nanoamps, so it's still very, very low. Then we have the shutdown mode. That was the one we were talking about on the previous slide. And you can see on the left-hand side, we show the wake-up time. So you can wake up from the shutdown mode, and the wake-up sources here are the reset pin, 5 IOs, and the RTC. And you can see the power consumption here is, again, very low. So 30 nanoamps without the RTC, 330 nanoamps with the RTC. A couple of standby modes, and these modes are without the 32 kbytes of SRAM on the top, and then with the 32 kbytes of SRAM on the bottom. In both cases, you can wake up in 40 microseconds, and the wake-up sources you see on the right, they build upon each other. So they're the wake-up sources for the shutdown mode plus these new wake-up sources. So in this case, it's the BOR and the watchdog. And you can see the power consumptions here go down to 130 nanoamps without the 32K of SRAM, and 360 nanoamps with the 32K of SRAM. Then we have a couple of stop modes, and you can see the wake-up time from these modes is either 4 microseconds or 5 microseconds. And on the right-hand side, you can see the wake-up sources. So again, they build upon the sources that are further up. So everything above that from the shutdown and standby modes, plus the wake-up sources are now all IOs in stop 2. PVD, the LCD, the comparators, the I2C, the low-power UART, and the low-power timer. And then stop mode 1, on top of that, you add all I2C and UART. And again, you can see the power consumptions here. So an excellent 1.1 microamp in stop mode 2, and then 7.3 microamps in stop mode 1, and then the power consumption with the RTCs on the right. Then we have the sleep mode, wakes up in a very fast six cycles, and the wake-up sources now are any event or interrupt. And you can see in the sleep mode, it's a very low 35 microamps per megahertz. And then finally, we have the run modes. And if you run the device up to 24 megahertz, then it's consuming 100 microamps per megahertz. If you run the device at full speed up to 80 megahertz, then it's 112 microamps per megahertz. So again, very good active power consumption modes. So with the STM32L4, we have a very unique combination of ultra-low power capability and performance. So you can see in the performance here on the left-hand side, we can reach 100 Drystone MIPS, or a very high 273 core mark from the STM32L4. But we're able to do that with a leadership number on the ULP bench as well. So the ULP bench is 153, and that's a benchmark that's been started to be used by more and more people in the ultra-low power space. So it's giving a very unique combination of performance and ultra-low power score on the benchmark as well. Another thing to note is it can wake up the device very, very fast. So it's not only important to have the low power modes, the stop and standby, and the run modes that we saw on the previous slides, so you can tune the performance of the microcontroller and the mode of the microcontroller to the application. But you also want to make sure that when you wake up from one of these low power modes, you're able to wake up very quickly, because you can use a lot of power consumption in the application if it takes quite a long time to wake the device up. So you can see here that if you go in the stop mode, from the stop mode to 48 megahertz takes less than 5 microseconds. And if you want to go all the way up to the full speed of the device, then it's still a very quick 20 microseconds to go from stop mode to 80 megahertz. On the right-hand side here, you can see the ultra-low power benchmark numbers. And what we're showing here is you can see the STM32L4 in the purple, and then you can see a couple of competitive devices, competitive device A and competitive device T. And today, the ULP bench numbers are published at 3 volts. So you see on the right of the chart, the x-axis here is the voltage. So you can see at 3 volts, the STM32L4 has an excellent number and compares very, very well with the leading ultra-low power microcontrollers in the marketplace. Remember, it's doing all of this with the very high performance levels that it's able to offer that these other microcontrollers cannot offer. Once you go to lower voltages, you can see that the STM32L4 gets even better, and you can see below 2.7 volts, the STM32L4 is the clear winner on the ULP benchmark. And that's significant because in reality, most low power applications are not operating at 3 volts, they're operating at a lower voltage. And so these lower voltage numbers are more relevant to most low power applications. And you can see that the STM32L4 continues to get better. A couple of other things to note. The other competitors are using DC to DC converters, and so you can see there's discontinuities as you go to lower voltages, and the DC to DC converter no longer works. So that as they go to lower voltages, not only do they fall behind the STM32L4, but they fall even further behind when their DC to DC converters no longer work. So when you start to look at the real range of an ultra-low power microcontroller and the voltages it's likely to be operating at, you can see that the STM32L4 is clearly the winner. And remember, it's doing all of that while offering the very high performance levels that you cannot see from these other microcontrollers. So let's look on how...
Stuart, sorry to interrupt you.
Hi,
everybody. Sure. We have a question regarding wake-up time. It's the question relative to the STM32F3. Regarding the wake-up time analysis, we have this kind of wake-up time analysis for STM32F3. Well, in fact, yeah. So for STM32F3, the number are slightly higher for wake-up time. So to give you an idea, we are in the range of 10 microseconds from stop mode, and we are in the range of 100 microseconds from standby. You can wake up at 8 megahertz. So there is no MSI. So again, the STM32L4 compared to the F3, the power consumption and the wake-up time is really optimized. So we can go from 0 to 80 megahertz in less than 20 microseconds. So it's really optimized. But this kind of data is available on the STM32F3. That's all. I'll give you the sorry.
No problem. So thank you. Thank you for the clarification. So on this slide, we're looking at the performance of the STM32L4, and typically with embedded microcontrollers, you're running from the internal flash. And the flash, once you get to the higher frequencies, is not able to supply data at the rate that the core is running at. So typically, you'll see that other microcontrollers start to add wait states as they go to the higher levels of performance. And if you look at the chart here, the gray line that you can see with the steps in it going up there would be a typical microcontroller. As you increase the frequency, you'll reach a point where it adds a wait state, so it drops down in performance, then it adds another wait state and it drops down in performance. And so as you go to the higher frequencies, you're not getting the full benefit of the microcontroller core. What you can see here is on the STM32L4, as you increase the frequency, it's a linear increase. So as we go up to 80 megahertz, the core mark performance continues to go up in the ratio of the increase of the clock speed. So in this case, we're getting the full performance out of the CortexM4 core when running at 80 megahertz. And we're able to do that with the ST Ultra-low. The Ultra-accelerator is a combination of a prefetch queue and branch caches, and it works very efficiently to make sure that you can run at full performance out of the internal flash memory, and you can see that from the core mark number that we're able to achieve here. So the core mark number we get is 273, and if you compare that to Sorry about that. It looks like my computer wanted to back up. If you compare that to the core mark number on the competitive ultra-low power devices, that's an order of magnitude higher than they're able to achieve. So it's a significant level of performance for an ultra-low power microcontroller. We're able to do that, of course, as I said, because of the ART accelerator and the fact that we're able to get the full performance out of the CortexM4 core with its FPU and its DSP instructions. In addition to that, some of the other things that help with performance is that we have 2 DMAs on the device, and they support up to 14 channels. So you can have DMA activity at the same time that the core is running, so further improving performance. And we have some high-speed communication interfaces on the device as well. So SPI will go up to 40 megabits, and the USART up to 10 megabits per second. So now we're going to look at some typical applications that the STM32L4 would make a good fit for. So we'll start with metering. Metering is an application where you would like to see a low power consumption in the microcontroller. And here we're talking about the range of meters. They could be electricity or gas meters, or they could be water meters, or they could be smart meters. So typically a meter is going to have a display on it. So we have built into the STM32L4 a segment LCD interface, so it'll drive 80 by 40 or 4 by 44 segment LCD, and so you're able to drive that directly from the device. We talked about it a little bit earlier, but within the VBAT domain as well, we also have an anti-tamper pin. So it's very important. You want to know if somebody's broken into the meter, so it's very important to have anti-tamper support, and that's built into the STM32L4. Meters are typically now, particularly in the smart meters now, going to have wireless functionality built in as well. And it tends to be a pretty broad range of wireless functionality depending on the meter, depending on the region as well. So the best way to support the wireless functionality is through these communication interfaces, through SPI, UART, or SDIO, and that makes it very easy to add the wireless communication protocol that you want for the application in the different regions and the different applications. We also have, you can see there's a lot of communication interfaces with the SPIs, and we have the quad SPI for external flash as well, and then a lot of UARTs and SDIO on the device as well. A meter is typically going to have buttons and relays in it as well, so there's a lot of fast IOs, up to 114 fast IOs available on the STM32L4. We've also got an external memory interface, so if you want to add more memory, then that's possible through this external memory interface, and that supports SRAM, PSRAM, NOR, and NAND. Quite often there's security requirements in meters as well. So we have a combination of hardware security acceleration on the device and a true random number generator as well. So it makes adding security easy into the metering application. We have the VBAT domain as well. Typically a meter may be stored before it's installed, and you want to maintain some parameters and the time, so you can do that with the VBAT domain on the device. And finally, the meters quite often have the requirement to measure very accurate external signals, and typically they would be up to 24-bit data that you're trying to read. So there's a digital filter that's been implemented on the STM32L4 that works with external sigma delta modulators. So you don't have to add a full sigma delta ADC to the application, but you can use a sigma delta modulator and then do the digital filtering on the device. So again, saving some cost, and also with the fact that you can do the digital filtering on the device, you can help save some power consumption as well, as that's been done in hardware. We'll now look at another application that's becoming very popular. I'm sure you've all seen the various fitness trackers that are appearing, and of course, healthcare and wellness is a growing, very rapidly growing market as well. So in this case, there may be a display, and in this case, it's probably going to be a TFT display. So we can drive those as well. We can either drive those with the external memory interface, which is a parallel interface to the TFT, or some of the TFT displays also have a SPI interface as well. So if it's that kind of TFT display, then we can drive it using the SPI. Most of these fitness trackers are going to have USB built into them as well, so we can do the we have the USB interface on the STM32L4. It's a USB on the go 2.0 full speed. It has the link power management and the battery charge detection as well, so it makes it well suited for these fitness kinds of applications. You may have an audio output from the fitness tracker as well. It could be to headphones or other audio devices. So in this case, we have two SAI serial audio interfaces on the device that allow you to add audio. Fitness trackers are typically going to be measuring external things like heart rate. And so in the case that you're trying to measure a small signal, then there's a built-in op-amp on the device. There's actually two of them, and they have built-in programmable gain amplifiers as well. So that helps amplify small external signals. And we have a good range of smart analog peripherals. So there's two 12-bit DACs, and we also have three 12-bit ADCs. They run up to 5 megasamples per second. And they also support as 16-bit resolution with hardware oversampling as well. And we'll go through it in a little bit more detail, but the power consumption numbers are also excellent as well on the ADC. There's a SWP interface as well, so if you want to add smart card to the application, it's possible with the SWP interface. Then there's a range of SPI and UARTs. Typically, these fitness trackers will have Bluetooth Low Energy built into them as well, so it's easy to add external Bluetooth Low Energy device using the SPI and UARTs. And also, there's going to be a lot of sensors, and of course, ST has an excellent range of sensors that are applicable in the fitness tracker space. And so it's possible to interface with those sensors using the I2C. And one of the features that we've also got on the STM32L4 was we have this batch acquisition mode, and what that allows is that you can collect the sensor data with the core without the core having to be running when using the batch acquisition mode, so it keeps the power consumption down. And when the sensor data is ready to be analyzed, you can wake up the core and analyze the data with the core quickly using the fast CortexM4 core, and then put the device back to sleep again. And finally, we can also use the digital filter in these applications as well. So typically, digital microphones are going to have a PDM output, and without the digital filter here, you would have to do PDM to PCM conversion, and that can be done in software, but it uses power consumption. So we can use the digital filter here to do the PDM to PCM conversion, and again, that helps keep the power consumption down on the in the actual application. So the next area we're going to look at is the industrial space, and there's a very broad range of industrial applications where low power is important as well. And again, the STM32L4 is a good fit in those spaces. So here, the segment LCD may well be applicable again, so we can use the built-in segment LCD controller. High temperature can also be important as well. So we have versions of the STM32L4 that work across a broad industrial temperature range from -40 up to 125 degrees C, so making it a good match for industrial applications. We have, of course, the broad range of SPI and UARTs, so 3 SPI and 6 UARTs, which again could be required in many industrial applications. I2C, we have 3 I2C. A lot of GPIOs, so again for buttons and relays, as we were talking about in the metering application. External memory interface if you want to add more memory. Security, that can be very important in industrial applications, so we have the true random number generator and the hardware encryption accelerator on the device. CAN is also used more and more in industrial applications, so we have support for CAN 2.0b active CAN, making it a good fit there as well. And then finally, we have advanced motor control timers on the device. We have 2 16-bit advanced motor control timers. So for industrial applications where motor control is important, we're able to support that as well. And of course, that's complemented by the 3 fast ADCs on the device as well for motor control applications. So we're going to look at the digital smart peripherals in a little bit more detail. And one of the things we've done, and one of the reasons we're calling them smart peripherals here, is these have been optimized to help with not only making sure you have the right peripheral set, but they're optimized for low power applications. So we have a low power UART that can wake the system, and it'll also make sure that while it's waking the system, it'll not lose the first bit of the data as well. Obviously, that's important. You want to wake it up from the low power UART, but you don't want to lose data. The I2C can also wake up the system when an address is detected. And we also have a low power timer that can count and generate events when you're in the low power modes. We have the quad SPI, so that allows easy addition of additional memory using the quad SPI flash, and that can be used for storing data, and it can also be used for executing code as well, so you can run code out of the external quad SPI. We have the digital filter, as we just said in both the metering and the fitness applications, that can either be used for an external signal delta modulator to give high resolution analog sensing capability. But it can also be used for the PDM to PCM conversion that you need with most digital microphones. And again, ST has a broad range of MEMS microphones that fit very well into these kind of applications. The peripheral clock is also independent from the main clock. So the benefit here is that you no longer are locked to running peripherals at a speed that matches up with the main system clock. So you can run the peripherals at the speed that makes sense for them, and the main system clock at the speed that makes sense for it, and therefore again able to optimize the power consumption. You don't have to have either of them running faster than they need to be running. And we have the single wire protocol, so if you have a need for smart cards in your application as well, that's supported through this single wire protocol. We also have a range of analog smart peripherals. So we have the 3 high-speed ADCs, the native 12-bit ADCs, and support up to 16-bit with hardware oversampling. And they run up to very high speeds as well, so 5 megasamples per second. But you can also see the power consumption is excellent as well. So if you go down to only 10 kilosamples per second, then it's consuming only 20 microamps. So you can have an ADC running in a low power application and be consuming a very small amount of power. We have the 2 op-amps, so if you're trying to sense very small external signals, then that's possible with the 2 op-amps with the built-in programmable gain amplifiers. 2 12-bit DACs, and they're capable of 1 megasample per second. And they also have the low-power sample and hold modes is available in stop modes. So in the stop mode, you can maintain an output.
Stuart, just 1 second. Hello again, Bertrand speaking. We have one question relative to the DAC, so that's why I interrupt you. The question is, what is the application of DAC in risk monitor you are showing in medical section? So, well, in fact, to answer this, you can use the DAC to measure, for example, the fat rate or the hydro rate. For example, to measure the fat rate, then you will use the DAC at a certain frequency and measure through the EDC. And by this way, you can measure the impedance of your body, and depending on the impedance of your body, you can then detect and measure the fat rate or the durometric rate. Depending on the frequency, you can either measure or the other. That's one of the example of waistband monitor that our customer are using.
So thank you, Bertrand.
Thank you.
So we also have two comparators, and they have low power modes, and they're also work in the stop mode. And finally, we have an internal voltage reference, so that can be programmable to either 2.048 or 2.5, and this can be used for external components, so you can supply that voltage to external components. So we've been through the core and the various peripherals on the device. So you can see we have the 80 megahertz Cortex-M4 core with the floating point, MPU, and ETM, the embedded trace. We have a broad range of connectivity, the USB, all the communication interfaces. We have available AES acceleration, the total random number generator, and the digital filter. And then on the bottom right, we have the advanced analog functionality. On the left, you can see we have the external memory interface, we have the LCD driver, and then we have up to 17 timers, including the 2 advanced motor control timers. And we have, depending on the package, up to 114 IOs, which also have some touch sensing capability as well. So you can see that it's a very, very capable device, and particularly with the large memories we have here. We have 1 meg of dual bank flash with error correction, and we have 128K of RAM. Yet all of this can fit into an extremely small form factor, so it fits in packages down to 4.4 by 3.8. So you can imagine in fitness trackers or other applications where a small form factor is important, you're getting a lot of functionality, but it's in a very small package size. So many of the low power applications also have high needs for both safety and security. So we're going to go through both the safety and security features on the device as well. So if we look at on the safety side, we have the brownout reset is available on in all modes. That's not true of all low power microcontrollers from our competitors. You'll find that the brownout reset is not available in some of the modes. We also have a clock security system, so if you lose an external clock, it's able to detect that and switch to an alternative clock. The SRAM has the internal SRAM has parity check on it. We have some backup byte registers. We also have supply monitoring, so you can make sure to monitor the status of the supplies. The flash memory has error correction, and it'll detect if there's an error. And finally, we have the dual watchdogs that you see on all of the STM32Ls, including an independent windowed watchdog. On the security side, we talked about it in the metering space. We have the anti-tamper detection. We have the MPU unit that allows to protect some areas of the memory. We have read-write protection available on the device. The device comes with a unique ID, and we also have the hardware encryption acceleration. There's a JTAG fuse that can be blown that can lock out access to the device, so people can't get in and read the device. And then we have the true random number generator. And finally, we have new on the STM32L4 software IP protection. So for people who have very critical IP that they want to protect, it's possible with the software IP protection on the L4 to do that. So I said at the beginning that ST has been a leader in the Cortex-M space from the very beginning of the Cortex-M space. So we started with the Cortex-M3s, and we expanded it to the M4s, the M0s, the M0 Pluses, and the M7s. So today we have a very broad portfolio of devices. You can see the high performance line at the top, which ranges from CortexM3, CortexM4, and most recently the CortexM7 devices, offering good range of speeds going from the 120 megahertz on the M3 up to 216 megahertz on the M7. We were the first company to announce an M7 product a year ago when ARM announced the core, and we were the first people to go into production with a Cortex M7 product, and we have that fully available with its complete ecosystem, as well as the L4 product we're talking about today. We have a range of mainstream CortexM microcontrollers based on the CortexM0, the M3, and the M4, and they go from 48 megahertz to 72 megahertz and give a very broad range of functionality there. And then in the ultra-low power space, we have an M3 device, the STM32L1. We have an M0 Plus device, the L0, and now with the L4, we've expanded the ultra-low power line to have a high performance, but still excellent with excellent low power modes with ultra-low power microcontroller.
Sorry, Stuart, I interrupt you for questions going back to the smart analog peripherals. The question is, how accurate is the internal voltage reference? Or minus 3 millivolts, so very accurate. In fact, the internal voltage reference, which can be used both for an internal ADC, DAC, operator, op amp, etc., is very accurate. So 3 millivolts maximum of accuracy. Again, all these data are available in the datasheet, which are available web. You will see the maximum value is what I'm telling you. So don't hesitate if you need more information to look at the datasheet. But basically, yes, the internal voltage reference is very accurate, and I think can be used in order to avoid to use external voltage reference and to decrease them. Thank you.
Thank you, Bertrand. So we were just starting to look at the ultra-low power portfolio. So the first device that we had in this portfolio was the STM32L1. That's a Cortex M3 device running up to 32 megahertz and comes with a wide variety of peripherals, including USB, LCD, true EEPROM, rich analog, dual blank flash, and you can see the memory options on these devices go from 32 to 512K bytes of flash with 80K of SRAM. Then we introduced the STM32L0, so that's an excellent ultra-low power microcontroller based on the Cortex M0 Plus core. That also operates at 32 megahertz and again has a good range of peripherals, smart peripherals on it. In the case of the STM32L0, we're expanding that portfolio so it goes from 16K of flash up to 192K of flash with 20K of SRAM. And then we have the STM32L4 that we're talking about today, and that takes the ultra-low power family up to very high levels of performance, but still with excellent power consumption, as you can see. And we now have the 80 megahertz Cortex M4 core with the floating point in the DSP, with all the analog and digital peripherals that we've been looking at, and the flash memory up from 256K bytes up to 1 megabyte of flash memory and 128K bytes of SRAM. So if we look at the L4 portfolio, as we just said, it goes from 256 to 1 mega flash. With 128K of SRAM. There's a broad range of packages, so you can see it goes from 64 LQFPs. There's a chip scale package there, which is a small form factor one at 4.4 by 3.8, and all the way up to LQFP 144 if you want access to all of the I/O and peripherals on the device. And then we have devices with the hardware encryption, so they're in the dark blue at the top. We talked about it in the presentation. We have the hardware encryption, and then the devices without the encryption are the light blue devices that you can see go from 256K to 1 mega flash. So at this point, I'm going to hand over to Alec Bath, who's going to talk you through the STM32L4 ecosystem.
Good morning, good afternoon. Again, I'm Alec Bath. I'm one of the field applications engineers for ST's microcontroller products. So let me switch my screen here. So here we see some of the ecosystem for hardware and software for the STM32L4. This is similar to our other products. Our hardware tools kind of come in a three-tier strategy. We have very low-cost Clio boards on the left, very small white board, around $10 US. In the middle, the Discovery Kit, which we'll be going into a little more detail on, which adds a lot more bells and whistles, MEMS, accelerometer, gyroscope, magnetometer, lots of fun audio things, a segment LCD display, USB support. Again, this is around $15 US. And then the full-featured evaluation board on the right, which covers all the peripherals of the L4. TFT display, a larger segment LCD display, supports CAN, the external memory interface. And then on the right, software tools, so the new STM32Cube ecosystem for configuring the device, creating code, doing power consumption calculations. And we'll take a look at that live today. So a little bit more on the Cube ecosystem. The Cube comes, there's two pieces. The Cube MX is the Windows-based tool, and then the Cube L4 is the library. This is similar to all of our other STM32 products, Cube F1, F2, F4, etc. So there's a hardware abstraction layer at the bottom. For the L4, we've also added a very lightweight, we call the low layer API. This is due to requests from previous customers who wanted something a little lighter weight API, so that includes that. Covers all the peripherals on board. Lots of middleware. Again, depending on the different families and what they include in hardware, the middleware will be slightly different. But we have USB host and device, graphic library, which is from Seger's MWin library. That's free. It's the STMWin. Open source FAT file system. The free RTOS, a real-time operating system. Lots and lots of examples. And then on top of that, you would place your user code.
Yeah, so Alex, there is a question related to that. So is there some reference code for all of the example given? So yeah, obviously, yes, the answer is yes. So there are thousands of example provided. You can, of course, it's available on st.com. You can have a look. There is an application note which, in fact, lists of examples available, and of course, you can download all the source code. Yeah, like, go on. Sorry.
Okay. So yes, and we'll I think a slide we have show the file tree of all the numerous examples for the different boards and peripherals. So taking a look at the discovery board here, on the top there's an integrated ST-Link V2-1 for programming and debugging. This is now incorporated in all our latest Nucleo boards, discovery boards, and full featured evaluation boards. 96 segment LCD, again driven directly from the L4. 9-axis motion MEMS, 3-axis accelerometer, gyroscope, magnetometer, so you can do a sensor fusion example. As well, on the bottom, a MEMS-based digital microphone, a 16 megabyte quad SPI NOR flash, push buttons, a couple of LEDs, and for doing USB on the go, connector on the bottom. For audio, again, on the right bottom, one of the ST digital microphones. There's also an audio codec, which will drive a 3.5 millimeter headphone jack. All the GPIOs are on the headers on the left and right sides. There's also, in addition to the STM32 on the top doing the debugging and the L4 target, there is a third STM32 on this board we call the MFX, and this is to measure power consumption in the various low power modes of the L4. It's non-intrusive, so can truly measure all the way down to the shutdown mode the current the L4 is drawing. And then once the L4 wakes up, this MFX chip will report back to the target over I2C what the measured current was and put it on the display, and we have a demo for that. On the back side of the discovery board, you can power the board off a CR2032 coin cell, or typically most customers will power it over the USB from the debugger on the top. Some of the examples that come out of the box for the discovery board, battery and current measurement. We can measure the voltage of the coin cell, power consumption, all the MFX-based current measurement of all the low power modes, a compass demo, a sound meter, audio record and playback via the MEMS microphone, and that's stored on the quad SPI flash, a fun guitar tuner you can check out. And I think Bertrand was going to show some of these, scroll through some of the demos. Did you want to do that?
Yeah, just to show it. Here is the example, for example, of a sound meter. So when I speak, there is a sound value changing and measuring it. Just to show that this demo, for example, just runs out of a small battery. Again, showing that it's really low power, but has a lot of performance as well. Okay, that's it.
So in addition to the discovery board, we have the Nucleo board. So the Nucleo board is, like all our other Nucleo boards, a very stripped down board, but still includes the ST-Link V2 debugger on the top. You notice it's perforated, so you can actually break off the debugger and use this for your own target application with the serial wire debug connections on the left and the header there. All the GPIOs are brought out on the outer headers. There's just 2 push buttons, one for user, one for reset. A couple of color LEDs. And then most interesting is it is Arduino compatible with the interconnectors, so a large number of shields from ST for Bluetooth, MEMS, motor control, lots and lots more are coming, and then lots of third-party Arduino shields will bolt on as well. So a brief look at CubeMX.
Sorry to interrupt you, Alex. So there is one question regarding where can I find the Disco install demo application source code. So yes, basically it is available on the STM32L4 Cube. So the application source code is available there. Another questions regarding STM Micro needs to push embed.org update to the latest embed lib, which fixes major problems with the invalid stack pointer. So we're working closely with ARM regarding all the embed sessions. So thanks for the heads up. So we'll check if there is something that we need to push the latest library from ARM. But of course, it will be done clean. And finally, we have a question regarding the Kyle. When the Kyle Microvision support the L4, well, in fact, it's already the case. The STM32L4 is fully supported by the Kyle Microvision. You can go on.
Okay, so STM32CubeMX. This is how some of the screens look, and I'm going to walk through this real time. So kind of breeze through this, but basically the first step is to select your microcontroller, whether it's an L4 or a different product, and you can filter by a variety of peripherals, packages, memory sizes, and other filters. And then configure the GPIO as well as the peripherals, any middleware, and then select from number of tool chains from IAR, Kyle, or GNU-based tools, and actually generate a full project right from CubeMX. And so I'm going to jump into a live demo here. Hopefully everyone can see that. So we open the CubeMX, click New Project. So we see we have 730 microcontrollers to choose from. We can filter by peripheral. Maybe we need the segment LCD. So now we're down to 100. We can filter by the series, L4. Now we're down to 19. The 476 in particular. If we need the big memory, so now we have 11 parts. And for our discovery board, this is using the LQFP100. So there she is. Double click on that, and that will launch another window. This is a Java-based tool, so you have to wait a few seconds occasionally and make sure that your Java is up to date. So here's our LQFP100 STM32L476 VG. We can zoom in and zoom out, move the part around. So for this example, we're gonna blink a couple of LEDs quickly. And on the discovery board, these are on PE8. We're going to set that as a GPIO output, and PB2. You can see the peripherals on the left here. If we have a couple of crystals, we can go in and enable those. And any other peripherals you're going to be using, maybe I2C. When we clicked on I2C, we see it populated PB6 and 7 here. So like other STM32s, there are alternate pins for most of the peripherals. So if we go on these pins and hold the control button down and click on them, we'll see other alternates highlighted in blue. Here we see PB8. So what we can do is actually drag this pin over, and it will now use that alternate one. Similarly for PB7. So that's some of the GPIO configuration details. The next tab we see here is clock configuration. So the L4 clock tree is quite complex. We have 5 clock sources, 2 low speed and 3 high speed. The part comes out of reset using the multi-speed internal RC oscillator at 4 megahertz, so that's 4,000 kilohertz. We'll crank that up to 32 megahertz here. We now see a clock mux here using either that MSI or an HSI, so this is a fixed 16 megahertz high-speed RC, or an external crystal, or we can route the MSI, HSI, or HSE through a PLL to reach the full 80 megahertz clock speed of the device. You can see a large number of the peripherals have their own, you can individually check where the clock source is coming from. So in addition to using the APB buses, which was typically the case, now we can maybe run UART3 from a lower speed clock source to reduce power, so forth. The next tab is the configuration tab. So now any of the peripherals we chose earlier will show up in these different boxes. So we had I2C1, that's under the connectivity box here. If we have an ADC selected, that'll show up on here. And then general system peripherals, GPIO, clocks, the interrupt controller, DMA controller, those selections would be made here. We click on the GPIO, we see our these are our 2 pins we selected for our LEDs. We highlight one, we can give that a name, so forth. Also, the pins related to peripherals like I2C we see here. If we want to use the internal pull-up, typical in I2C, we can select that here. And then the pins related to the external crystals. So we'll click OK. The last tab is the power consumption calculator. So we'll go through this in just a minute here. So the next step is typically making some project settings. Give your project a name, where you want to put it.
Sorry to interrupt you. There are questions regarding the clock.
Okay.
The question is, besides getting a higher system clock speed, what other advantages are there with using the PLL? Well, not really some interest. I mean, if, for example, if you use the audio, then the audio interface are linked to our separated PLL, for example, for audio. It means, one interest, you can run your whole system at one frequency, while you can adapt all your audio at an independent frequency. That's the only advantage I see. Of course, you can get a higher system clock. For example, if you want to use USB, then, and if you have a 32 kilohertz, you don't need a dedicated crystal. So there is no real advantage to use a PLL. Of course, there is a kind of penalty when using the PLL, even if the power consumption of the PLL is quite small. We have optimized it a lot on this product. But basically, yes, if you can run up, I mean, if you can just consider to go up to 48 megahertz, then you don't need to use a PLL, except for the audio, where it can be interesting to have separate audio frequencies. And also, I'm going to answer to one other question: what is the difference between Nucleo and Discovery Kit? Both looks alike, the same functionality. Well, not really. So here is the Nucleo. As you can see, it's very minimum, as Alec showed to you. There is mainly the product. You have a connection to every every signal, the Arduino connector, and also all the signals are available here. And there is the ST link for debug. That's it. There is no more. There is a 32 kHz crystal here, and that's it. And if you compare to this one, well, it's more full features. It's this one. There's a lot of more features: LCD, magnetometer, audio, microphone, lot of connector. So it's really, and to give you an idea, the recommended resale price for this one is about $10, and this one is about $19. So it's about the double of price. But yes, you have a lot of flexibility. Either you can use this one, which provides a lot of flexibility. This one where we have already a lot of components on boards. Thank you, Alec. You can go on, sorry.
Okay, thank you, Bertrand. So yes, on the left you can see the different PLL blocks. So if your system does not need to use the PLL, then yeah, it is advantageous, for instance, to use the MSI up to 48 megahertz. You'll have the fastest wake-up times and save a little bit of power due to the latency involved with restarting the PLL. And then the other two blocks we saw here for that serial audio interface. So again, our project settings, give our project a name. Here are the tool chains, IAR EWARM, two of the Kyle tool chains, Italic's GNU-based True Studio, and the new Open STM32 AC6 based GNU tool chain as well. If you do not have the Cube L4 HAL library loaded, when you try to build your code, it will automatically attempt to download that for you, and this is the version it's using. You have a few options for code generation here. So once we do this, we can click on the little gear here, generate our source code, generate our IAR project, and right from CubeMX, open IAR, launch the workspace. And here we see several folders for the different HAL libraries, the SimSys library from ARM. So it's going to pull in all the source code it needs for this particular project. We can double click on the C file, see it here. Actually set up the clocks for us as we chose. Our I2C interface, our GPIO, and then we'll just have an empty while loop here. So I have some magical code I can paste in here to toggle the PB2 and PE8 GPIO pins, HAL delay, 200 millisecond delay using the SysTick timer. And now we just make the project. And this will take a few seconds here.
Meanwhile, there is a question for you, Alec.
Okay.
Will CubeMX ever support Relays Crosswalks IDE? It is a GCC-based IDE. I'll let you answer on this one.
Was that Kucox?
No. Relay Crosswalks.
It should support most of the Eclipse GNU framework should be the same. The only thing might be the debug and flash programming support for the L4 we've had Rowley support for other STM32 products, so I'm assuming it's coming for the L4 as well. I'm not positive on the status for Rowley. Okay, so we have our project built, no errors, no warnings. We can download and debug. Uh-oh. Make sure all our settings are correct here. I know why my board went to sleep. So now we have our code running on our board and our magic dancing LEDs. So a simple example, but I'll show you the steps from CubeMX, a few selections, generating a project, and debugging and programming.
Okay, so there are several questions. Is the high performance light weight low layer, the LL APIs, a new name for the old standard peripheral libraries? Is these are not the same? Are there any plans to support standard peripheral library as standalone component for the STM32L4 family? So yes, let's say that it's not exactly the same as the standard peripheral libraries, but yes, it's really similar. I mean, we can do both. Use at the same time the HAL and the LL API. I develop under Linux. CubeMX can also run on Linux since it is Java. Yes. Apparently, it supports also the Open STM32 Workbench working on Linux, but there are many problems when trying to compile due to includes. Can you show a tutorial for it? Well, we cannot show it now, but well, that's something that could be done by Google Hangout for sure. Other questions regarding which option would offer better power consumption at the same speed, external or internal clock. So the internal clock are really optimized, especially the MSI is really optimized. So for example, the MSI can be programmed from 100K up to 48 megahertz. And the power consumption is linear, or I mean, yeah, it's really optimized depending on the frequency that you are using. So the internal clock is really optimized. Let's say that there will be not the big difference if you use external or internal clock. I mean, the device is of course is to not be obliged to use external clock, but let's say there will not be a lot of difference. There is also another question regarding the clock. If I am using USB application, then do I need to use Crystal? If you use a 32.768 kHz, so watch Crystal, RTC for example, then you don't need to use a dedicated Crystal. Okay. If you don't have a 32 kHz crystals in your design, yes, you need a crystal, either a high-speed crystal or a low-speed crystal. A question regarding the are the reference design for this development boards available in the various project files time to edit for our own boards? Yes, so it's available in CatStar. It's available on st.com. You can download the CatStar project, but we don't provide the project in all files type available in the market. Can I use Eclipse for this? Yes, you can use Eclipse, as Alex said. The question regarding the ADC, can the ADC directly utilize the voltage reference, or does the ADC always measure relative to VDD, such that the software has to measure the reference simultaneously to the signals and calculate the actual voltage? In fact, no, you don't have to do it. I mean, you use a voltage, internal voltage reference, and that's it. I mean, as I said previously, the internal voltage reference is very accurate. Or you can use also, there is a VRF pin that you can connect to either an external voltage reference or to VDD if you want. It's up to you. If you want to, if you want to use a voltage reference, an internal voltage reference, then it's very accurate, and you don't need to monitor both the voltage reference, because it will be your reference width. Is it possible to use DFU for device programming? Yes, of course, yes. It's a bootloader. You can program the device either through DFUs or USB or USPI or I2C or UART or CAN even. So a lot of flexibility to program this device. Question regarding the seminar in China. Yes, but in fact the seminar in China already occurred last month. More than 3,000 attendees across 12 cities. So as Stuart said, of the possibility to attend to a US seminar so you can check on st.com, and also, by the way, there will be a Europe seminar starting from November. So don't hesitate, stay tuned. There will be also invitation to participate to Europe seminar. Is Microcell Linux will support for this board? Well, we don't have a plan for that now, but yes, obviously that's something which is possible. If you see some interest, let us know. That's something that we can do for sure. What is the roadmap availability of LQFP 48 parts in the L4 family? So it will come soon. I cannot comment regarding the roadmap, but yes, as you can imagine, the STM32L4 family will grow very quickly in the, let's say, next year. Let's say. So stay tuned. Question regarding competition. Ambiq Micro claimed that their Apollo Ultra-low Power Microcontroller is beating in energy consumption all existing low power microcontrollers by a factor of 10. Can you comment on that and compare your STM32L4 to the Apollo? Yeah, sure, but I've not seen any part or datasheet of this product, so it's difficult for me to comment. Let's say that the STM32L4 is fully in production, everything is available, so I cannot comment about this part. Another question, does the STM32L4 support the embedded trace macrocell for debugging as well? Yes, exactly, yeah. It is fully supported, so what we call the ETM is available on STM32L4 for all the package. Also, I would like to notice that there is STM32L4 online training, so available both in PDF but also in video. I think you can have a look. It's very interesting, and you can select. There is 44 chapter parts, and you can have a look of what you would like to know. Of course, there is, as you know, forum, so don't hesitate to also use this community for this, for any questions. That's all. I don't think you have another question. Is it possible to have a dual boot with this board? So this is a question related to possibility of flashing the memory using the same STM32L4. Dual boot with board. I'm not sure I understand the question.
The dual bank flash could be used, perhaps.
Yeah. So yes, there is dual bank here. So yes, that's if it is the question is yes. Are you planning support the open source CookOps? So CookOps is available. Huh? The support for CookOps is available now. Can look on CookOps site, but everything is available. I think we need to close now. Natalie, I give you.
Thank you. Yeah, I think what we will do is we will put all the link to the training, the video, and the forum. And if people now we will have to close because it's 1 hour 20. I'd like to thank everybody for joining and you. And if people have questions, they can use the forum on st.com or the page for the Google Hangout. And as mentioned, we will post the link to the additional material. So we'll close here, and thank you to everyone.
Thanks for watching. Thank you.
Thank you. Bye.
Bye-bye.